Now for this last problem, I think the choice of your control volume, this is where it is the most, where it is the trickiest. But again, there are a few bounds of your control volumes which should stand out directly. So the problem talks about relating the momentum thickness, which is an integral between 0 and infinity of a certain function of the velocity at a given position x. So it makes sense that the bounds of your certain bounds of your control volumes will be lines of a given x, right? Because these are the lines along which you will evaluate the integral that gives the momentum thickness, right? And again, you want to take the bounds of your integral of your control volume where you know stuff, right? And since you are interested in the momentum thickness at x, taking this bound makes sense, and you're relating, and you want to relate that to the drag between 0 and x. So it kind of makes sense that the bound of your control volumes will be at x equals 0 and at x. Now, another obvious bound for your control volume, and this is quite general, is this bound here, right? And why do you want to take this as a bound for your control volume? Well, you have to relate it to the drag onto the plate, right? So the drag onto the plate will be the integral of the stress tensor dotted on the tangential direction along this surface here, right? So the total drag will come in naturally once you impose the momentum equation onto the control volume, if this is one of the bound of your control volume. Okay, now the difficult boundary is where do you stop this control volume? Now, what you don't want to do in general is to have a control volume which extends to infinity, right? Even though your integral for the momentum balance goes to infinity, it's not a good idea to have a control volume which is infinite, because just think of it, here you will compute the flux of momentum, for instance, out of this surface. You will take the flux of momentum out of this surface here, and you'll take the difference. But then you have a quantity which is infinity minus a quantity which is infinity, and you can't say much about that because this is not determined. So you don't want to take a control volume which is infinite. Now, the most obvious choice for a control volume, what you would do is simply to take here a rectangular control volume, right? That would be a natural choice. It turns out that here this is not the right choice, and let me explain you why. The general principle is that you want to take a boundary here where you know the most things, where you know what is happening. And if you take a straight boundary on the top for your control volume, well, there is something which you do not know, and it's not obvious from the picture. So let me just take a step back and think about mass conservation, right? So here you have at the inlet of your control volume, you have a uniform velocity profile, right? And the velocity here on the top is roughly capital U. And at the outlet, well, you don't have a uniform profile, right? You have this boundary layer here, and at the top, the velocity will be roughly capital U. And if anything, it will be slightly smaller than capital U. So it should be clear that you have more mass coming from the inlet. If you take a constant height here, you have more mass coming from the inlet than mass coming out of the inlet. You have a deficit of mass coming out of the inlet, which means that you have mass leaking a bit through the top of your surface, right? Therefore, and what that means is simply that the streamlines are not straight here, right? Actually, the streamline will be slightly bent like this, because you have this mass deficit. And therefore, if you pick a top the top surface of your control volume to be straight, then you will have to take into account when you do the mass conservation and when you do momentum conservation, you will have to take into account the fact that you have momentum and mass leaking through the top surface, and that will make the integral complicated because you don't know exactly the details of your streamline. In fact, you're not given you're not giving the stream function or the streamlines, and you're not even given in that problem the shape of your velocity profile here. So that will be a tough one. And therefore, since you want to pick a surface where you know the most things, what you actually want to pick in that case is a streamline. Right? You want to pick, even though you don't know what the streamline is, you can always just decide that the top surface here is going to be a streamline. And the advantage of doing that is that, well, if your top surface here is a streamline, then there is no mass flux coming out of your control volume, right? So that by picking this control volume here, this allows you to have mass fluxes or volumetric flow rates only through the inlet and the outlet. And because you decided that your top surface was a streamline, then therefore you don't have any mass flux out of the top surface. So if you do that, then you do have to give names. And here, what we'll say is we'll just call this height at the inlet h naught. And we don't know what the height of the outlet is, but we'll call it simply hx. And it's going to be slightly higher than h naught. Okay, so with that, I think you should be able to finish off the problem.